Okay, the next paper is also from Alibaba. So the speaker is Tao Lin. He's a senior staff engineer and director in the network R&D team at Alibaba Cloud, leading the network automation team. His interests lie in the design, development, and the stabilization of large-scale distributed systems. He received his BS from Tsinghua University, PhD from Virginia Tech, and was a postdoctoral researcher at McMaster's University. Yeah, please.
Thank you very much. Hello, everyone. I'm Tao, and I'm honored to present our work, SkyNet. It is a joint effort from my team, another team, and some other team from Alibaba Cloud. How about now? Yeah, sorry. Okay, let me start again. Hello, everyone. I'm Tao, coming from Alibaba Cloud, and I'm honored to present our work, SkyNet. It's a joint effort from my team, Annan's team, and some other team from Alibaba Cloud. And the first three authors are co-primary authors. So I will first cover the problem statement. Please allow me to start with some context. So we are a team to manage Alibaba network infrastructure. On top of this large-scale network service, we run several key businesses, which include e-commerce and cloud and map and instant payment, etc. So as we can tell, a stable service plays a key role for all this business. And as also we know, from time to time, network incident happens. So on the left-hand side, we show our observation over different root causes happening in our network. And on the right-hand side, a study shows that among all these incidents, only a small portion are considered severe or critical incidents, but they cause the most financial loss or reputation damages. So in order to address both, left-hand side, these minor common network issues, and also on the right-hand side, severe network outage, we need to monitor the live system. And on this page, left-hand side, which shows a simple example of network diagram with several incidents going on. And the right-hand side, we have a list of monitoring tools. We evaluate their performance over time, and clearly with single tool itself, it cannot cover 100% network incidents. We also look into the existing works. We see most of them focus on approaches with one data source. Intuitively, we can try to integrate all this tool and try to address the coverage issue, which work out well in most cases. However, when there are severe network failure, we see tons of alerts flooding through our system. Basically, here is the contradiction part. The more tools fine-tuned or integrated, actually the worse the alert floods. We have a production number. We saw once over 10K alerts generated within minutes flash throughout our pipeline. And even worse, we have three challenges we observed. The first one, the root cause can trigger alerts, but these alerts might be reported after others, potentially can mislead our operators. The reason being some system has this sample interval, calculation interval, report interval, and this time gap raised against the actual time when root cause happens. And second challenge is, sometimes we saw multiple incidents happen at the same time. Our operators may overlook some of them simply because these alerts vary in the flood of alerts. And the third challenge is, even if our operator knows there are parallel incidents, they often struggle to determine which one has higher priority. And as I mentioned earlier, this severe network outage can cause a lot of, very expensive. So people are under time pressure, and then to make decisions to address all three in a timely, constrained manner. So it's very challenging job for them. So here is the problem statement. On the left-hand side, we show the existing works, mainly focused on minor failures with known symptom and reasonable alert volume, and also user can prepare automatic standard operation procedure, SOPs. On the right-hand side, we have our challenge. These severe failures are rare, unprecedented, and cause a lot of financial loss and also reputation damage. It comes with huge amount of alerts. And most of the time, we had to manually triage them and under the time pressure. So in order to address this problem, we had to first define our goals. So high-level design, in case of the severe network outage, we want to be able to mark out the failure scope, extract readable information out of the flood. We also want to help operators to respond quickly. Once this happens, we need to notify them, and also they need to know how to prioritize their limited resource to handle this efficiently. And a low-level design with more specific requirements. The first two automatically discover those incidents, and the second one is to identify the root cause if possible, are basic requirements. In case of a flood of alerts, operator also want us to reduce alerts to a limited number, let's say 20, which is consumable, and then narrow down the failure zones, and also evaluate impacts, suggest priorities. This is what our operators want, and then this is also our product, SkyNet output. On the right-hand side, I showed example of text output, and from top to bottom shows two instances. One has a risk score 60. I'm going to explain this risk score later. And with the location, start time, end time, and the list of compressed alerts associated with this instance. Similarly, instance 2 also has this field information. So here is our solution, SkyNet. On the right-hand side, the three dark blue boxes shows the key components, preprocessor, locator, and evaluator. Preprocessor consume flood of alerts and compress them, generate structured data. Locator tell us how many instances are running in parallel. And also, it is responsible to raise hand if it detects one of the instances actually is a severe network outage. So they need to notify and get attention right away. An evaluator tell us the priority among all instances. So this is just give the top-level idea. I'm going to cover these three key components one at a time. First, preprocessor. The key idea is that we need to standardize all these outputs generated by different monitoring tools. Because these tools, they have their own pace, they have their own schema. So first thing is we want to keep minimum information, like what, when, and where, when we receive an alert. And in order to further reduce the volume of the alerts, we also do some considerations. So I show three examples here. Example on the left, if they are identical, we compress them. And the example in middle, if they come from a single data source and they talk about similar things, we consolidate them into one. And then the example on the right, if they come from diverse data sources, we can also consider it if they are talking about similar things. So by doing so, we reduce these alert floods dramatically. So previously, we saw like over 200K alerts per hour. And after this preprocessor, we have under 10K alerts under normal conditions. And even in this extreme circumstance, we see no more than 50K. So at this stage, this number is consumable by our normal system. So we stop at here. We don't continue to compress them. Now we go through the next key component, locator. The key idea is we observe the network alerts or outage propagate through topology links. It can be physical links. It can be logical links, like a protocol. I use a live example to illustrate the idea. First, we see the left-hand side, we have a SMP alert, and this is first one, so we create a record, incident 1. And second alert comes, and we check the location, they are not connected to each other, so we create a new incident, incident 2. Now the third and the fourth alert comes, their locations are connected to the one that associated with incident 2, so we expand incident 2's scope and attach these two alerts to incident 2 instead of we created a new instance. So as we can see, we already have 4 alerts, but only generate 2 incident records. This shows the idea of how we isolate instance, and this addresses the first 2 challenges I mentioned earlier. Consider the root cause alerts come later, and it will either join an existing incident or it can merge several incidents together because these alerts become the center point to connect all the existing instances. And this also gives us a hint. We can use a page ranking like algorithm to vote which one looks like the root cause of this incident. And the second challenge was our operators might overlook some of the incidents, but now it's clear. Although we have a list of alerts on the left-hand side, but clearly we only see 2 incidents on the right-hand side. Now, we need to answer another question. When are we going to declare this is like a red alert? We see a very serious network outage. So this algorithm should not miss any real serious outage. So our organization goal is when we try to determine whether instance is a serious one, we should not miss anyone. So 0 false negative. And we can allow few false positive cases. And here's our approach. We define a threshold. Before we go into detail of the threshold, we want to define 3 different layers of alerts: failure alerts, abnormal alerts, root cause alerts. Failure alerts represent what user experience, like the ping, end-to-end ping, for example. Abnormal alerts usually refer to internal states, which is not right. And root cause is knowing, let's say, hardware failure or system auto OM. And we use the 3 tuple. You can see on the bottom, threshold with 3 A, B, C. A is BIZ, represent number of failure alerts. And then B represent number of failure alerts plus other alerts, the number of other alerts. And then the third one, O, means we just simply count the total number. In our production, we come up with this combined setting. 2 means if we see 2 failure alerts, we consider this as a severe network outage. Or we see 1 plus 2 others. We also consider this as a severe network outage. And the last one is we see total alerts exceed 5. We can also raise hand. So now we go through the right-hand side example. Incident 1 only has 1 alert, so it's not a serious outage. However, incident 2, the first one is ping, so which match the failure alerts. So we have 1, and we have syslog and out of band, so it's 1 plus 2. We meet the center, the 3 tuple, the B field become true, so we believe this is a serious incident. We will raise our hand. So far, we went through preprocessor and locator. It gave us the first innovation. We consume flood alerts and then generate a limited number of network instances. And we also can tell whether they are serious or not. Now, the third part, evaluator. Due to time limitation, I'm not going through the detail of this equation, but basically it's the penalty function. Whenever a user prefer those metrics, if they degrade, we increase the penalty. On the other hand, if user try to avoid something, those metrics increase, we also increase the penalty. I will just give one example, like time. If this instance didn't get addressed within a short period of time, we increase the penalty. Or if there is a key customer behind this instance, then we also increase the penalty. So back to our previous example, we have a risk score 60 for one instance and 9.5 for the other. Now we can conclude that the output looks like our network operators see the report with 2 parallel instances, and where are they and where did they start. Also, incident 1 is more critical. If they have limited resource, better look into incident 1 first. So evaluator give us the second innovation. We can give the suggestion which one has higher priority, more urgent. We run this system in production for 1.5 years and 0 false negative as expected. We also see the mitigation time reduced like 80%. Here we did another study. On the left-hand side, we try to integrate different number of data sources and see the behavior of SkyNet. Interesting thing is we see now we want all data sources to be integrated, which give the best result. Remember the contradiction at the beginning I mentioned. For minor cases, we want more data sources, but for flood alerts, we don't prefer more data sources. And this study shows now we turn things around. Our goals now are consistent. We both want more data sources to be integrated. And then there's a brief discussion, why not LLM? At the time when we designed and developed SkyNet, without preprocessor, the volume of the alerts can easily exceed the LLM's input capacity. And also, because LLM function act like a black box at a time, we were worried whether they will mislead us. So actually, in our teams, we actually do things in parallel. We go with SkyNet and also go with the LLM approach, the previous paper, and use them as a backup. We have a last page. We show a real case. There's an internet entrance break outage. In this one, BGP link down comes up first. However, our system can adjust to link break as the root cause shortly. We actually, this failure was done within 10 minutes, but actually, if you look at the risk score curve, it's a little bit over 10 minutes because some 2-minute long tail. This is because we had to work with our partner outside our company, so it takes a while. But in the past, without SkyNet, a similar one cost us several hours. So this is one example showing that it does function well as expected in our production. And thank you very much for the listening, and I'm open to questions, suggestions, discussions.
Okay, any questions from the audience? Well, I think it's a really interesting talk, and I have a few questions. Let me look at my notes here. So in very early part of your slides, you have a problem I think is very interesting. That is the root cause alerts that actually happens after the other alerts, right? But later in the talk, I didn't see how you solve this problem. Could you explain more on this?
Oh, a very good question. Actually, this approach, SkyNet, does not care exactly instant different types. You just count, simply count. So this is like in additional, we have another system which will handle predefined instance based on the root causes, for example. But this one just based on the pattern. So it's just like the safety net at the bottom. So it does not really differentiate which kind of instance it is. Yeah.
I see. Still no question from the audience? Okay, let me ask another one. So the first technique that you talk about is grouping the alerts, right? So can you talk about more, another case that you didn't mention is the end-to-end user experience, like great failure. People are experiencing downgraded bandwidth, for example, but there's no alerts in the system. So can you elaborate on how do you solve this? Or do you concern about
Sorry,
this?
there's some echo. Can you come closer? I cannot hear your question.
Yeah. So the problem is about grade failure. That there's degraded services, but there's no alerts from the system.
Sorry, I still cannot. The echo is really big. So.
Okay.
Sorry. We can talk about this offline.
We can talk about this offline. Yeah. So any?
There's a question in the audience.
Yeah. Thanks very much for a great talk. One question, you mentioned that LLM-based solution could be useful in the same kind of setting of the problems. Could you explain a little bit more? Thank you.
Oh, sure. Actually, the previous paper talking about LLM that presented, that's also from our group. So that's a different approach. This SkyNet is like more deterministic system implemented. So there's a boundary between automation and intelligence. So we are working on both. But we don't want to merge them because at this stage, we want a confident solution. So we do backup. So one approach and the other one in parallel, they back up each other without merging. That's our strategy for now. Yeah, thank you.
Okay.